morning, good afternoon, and good evening to you all, wherever you are. Welcome to today's free KLIPPEL webinar, which continues our discussion of acoustical measurement of sound system equipment according to IEC 60268-21. My name is Kent Peterson, and I'm broadcasting from Warquin in St. Paul, Minnesota, your North American home of KLIPPEL sales and technical support. I hope you are all doing well and maintaining a healthy mind, getting out and enjoying the weather, and taking time such as this to better your knowledge. There sure is ample opportunity. Today's topic is simulating a standard condition at a single evaluation point. As always, we're joined by Dr. Wolfgang KLIPPEL and Mr. Christian Bellman to discuss these techniques. Today should be fun as we have plenty of real-time measurements. This should stretch our knowledge of online technical issues nicely. It's going to be fun. As you can see for this webinar, we're trying Zoom. The last program we used did not really provide us with some of the features we were hoping for, so we're going to give this a run. As always, please locate your chat window and let us know if you have any problems. Hopefully we can fix them. In Zoom, there are separate panels for polls and questions as well. These are located, or should be located, at the bottom of your screen in the program. Send along your questions in that particular Q&A window for after the lecture, and so that we can keep them stacked in order of appearance. Okay, let's get going. Let me turn it over to Dr. Wolfgang KLIPPEL and Mr. Christian Bellman, and we'll all get together and talk after the lecture. Gentlemen, take it away.
Hello, everybody. Before I start with this interesting session, I would like to give a very short overview on the previous ones. We started with the introduction about the acoustical output-based testing, and then I have spoken about problems if we have active systems that the transfer depends on the controllers, and we have many input channels and so on. Christian showed us how to do measurements of the 3D output with the holographic scanning, and finally we have spoken in the last session how to interpret the data. Now we have everything together to use this data here in my room to generate simulated standard condition at one single point. Yeah, and what means that we would like to show that standard measurements can be performed in such a room, so we can simplify this by creating artificially free field and R field condition. That's supported by the standard. To be more precise, we would like to compensate here for the room reflection, different positioning, and the distance. Yeah, and the key for that is generating a room compensation function. But you will see. But we start first with an interesting poll. When I was a student at the university and I had to do some measurements, usually I had to wait that I get access to the Anechoic Room because other students and some assistant professors would like to do their measurement first. I assume it's the same with you. Please use this poll to say, yes, I have to wait, it hinders my work. And choose here between not really, sometimes, usually, frequently, and always. I don't see my poll. Ah, yes, it comes. Yeah, there's still some data coming. At the moment, I see that the times has changed. So that means about 30% say it's not really a problem. We have the opportunity for doing that. Others say sometimes and frequently and always together are less than 30%. Okay, that's a very short information for that. We are searching today for an alternative for that. What is our target? Simulated far field and free field condition at one point only. And to do fast measurements. That means we have not the time for doing scanning, holographic measurements. We would like to do a lot of simple distortion measurements and other measurements at one point. A minimum equipment, one microphone, and of course, we would like to support other measurements like nonlinear distortion measurement, compression, and tuning DSP. And of course, later on, we will use the same technology for decompose more or less the sound field here at my ear and to use that for perceptual evaluation. Yeah, here are three different techniques. First is the time windowing. We have spoken about that. It's a powerful technique, but it fails at low frequencies. Then in the second session, we have spoken about the new holographic measurement. That's quite nice. At very low frequencies, it is very precise, but you need some robotics and you need some scanning time for doing that. So it takes some time. And now today we are focusing using the data from time windowing and from the holographic measurement or other similar techniques like a ground floor measurement outside to generate compensation functions. So that is only applicable for one point. It's a very fast way for doing that. We are doing this in a new way by generating a complex compensation function, which is used as a filter just after the microphone. So that's new. And we need some accurate reference information. Yeah, we will not only compensate for the room reflections, we will also compensate for the wrong distance. That means our microphone will be in the near field, where usually the data are not really valid. So we have here a distance for my speaker of 30 centimeters, and we would like to make an accurate far field extrapolation. This cannot be done by the 1 divided by r law. We have to use here the solution from the spherical wave modeling. So that's more or less a holographic measurement technique based on the spherical waves. Of course, we need usually some scanning data from that. Also here, the compensation function applied to that would simplify this process dramatically. So it's, again, we are using a subset for that for realizing one-point measurements. And we end up again with a complex transfer function for compensating for the distance. But we need reference information. Yeah, this is my room here. You see it later on live. What is the problem? Here is a small JBL Bluetooth speaker. There's a very small distance to my laptop. I cannot avoid that. Then are coming the walls, and we have a half space measurement. I'm using my table as a half space. Yeah, and the distance is quite close. And I have the following problems. My room is still not large. So that means the distance to the walls, to the ceiling is less than 1.5 meters. So I get some early reflection that limits my windowing. I have a typical reverberation time of half a second. So that is not so bad. I have enough books here and I have a carpet, some chairs, but that's it. No, that's not a good treatment. And I have a large table, but it's not large enough to have an infinite half space. So it's only 80 centimeters, 70 centimeters away from the speaker. That's it. That are the problems. And maybe I have some ambient noise from outside. There's a music school, or here from here the office. How can we do the best out of that? What are the consequences? I have a small room, a small distance. I need a very short window. That limits my resolution below 500 Hertz. Actually, I can forget the data below 500 Hertz. I used a reasonable distance of 30 centimeters from the loudspeaker just to, that's just the optimum value between, here's the reflections from my laptop and other points. We are at higher frequencies already in the far field, but not below 200 Hertz. Christian has shown that here in session 2 already. So we can do some far field prediction with the 1 divided by R law at higher frequencies, that's fine, but at lower frequencies, we search for a new solution. Yeah, how can we handle the reverberation time? We will see some room modes. They will affect very much our low frequency band, our low frequency response. And maybe we can solve this with complex filtering of the microphone signal. Then we have here our limited ground floor measurement. We get some reflection from the edges. That's why I put actually the microphone in the middle of the table to minimize that. Yeah, and I have to use a short distance, 30 centimeters is quite good to have a good suppression of any noise from outside. Yeah. Now let's model the speaker and the room position before we are generating our room correction curve. Here's our stimulus. That's our room loudspeaker room microphone system that indicates that we have some room reflections. Our microphone is at a fixed position. Actually, with a tape, I mounted the microphone on the table. We call that test point. It's in the near field. Okay, and here you see how we are modeling that. We have actually here our linear direct sound model. It has for the linear part, for the linear signal P lin, we have here a linear system H3, which just models that. Up to the evaluation point, which is usually at 1 meter. So RE is not the measurement point from the microphone. It is actually the optimal evaluation point. And here we get also our distortion from our speaker. If the speaker generates some distortions at higher amplitudes. Okay, and that's actually our desired signal here. That's the free field response in the free field sound pressure. But unfortunately, we have here our room influence. So we have an undesired second linear system, which generates the near field sound pressure signal here at the test point. Okay, here I have spoken already, the speaker generates a nonlinear distortion, that's harmonics, intermodulation, distortion, rub and bass. But we would like to generate accurate data here at the evaluation point. In other words, we would like to get rid of the unnecessary, undesired room transfer function. Yeah, and we would like, sorry, I was too fast. We would like to compensate for the distance of the 2 points. Yeah, the ISC standard provides actually 2 solutions for that. One is very old and very common. You are doing in a normal way your far field measurement, you get a sound pressure response, and you just compensate here for the room influence in the fundamental response by adding normal scalar, not complex transfer function or correction curve to that. Here you see the correction is just added to the level of the sound pressure level, SPL level, after the analysis. So that's one way, and that's always real values, dB values, relative simple, no? Used for generating a room correction function. Unfortunately, this way cannot used for harmonic distortion measurement, especially it cannot fix the problem if we are using the Farina technique with the chirp. But the standard provides a second method, and that corrects directly the problem at the root cause. That's just after the microphone, we are inserting here a complex filter, which transforms more or less the measured sound pressure signal at the test point to maybe a second point in the far field at 1 meter, by compensating also for the room reflections. And then we can apply any analysis from different measurement modules to get standard results. So that's quite interesting. You can apply it for nonlinear distortion measurement, and we are generating free field and far field condition artificially. Yeah, and it can be applied to Farina. Now we are on the next pole. I assume many of you are using already the first method. That means just making a scalar correction curve for your sound pressure fundamental response. Please choose yes and no. So let's see. Oh, at the moment it's 50-50. Now we are getting more no and less yes. So I think it's now finished. I don't know whether you see it or now you see it. 40% yes, and the other one is about 60% no. Some words to that. If you have a large room, you are working with the same speakers or similar speakers, since such a room correction curve has a big value. From time to time, you have to check that. Maybe you have to create different room correction curves for different applications, especially if they are completely different loudspeakers are used. But the microphone position and the loudspeaker position is usually well defined. Everything is quite nicely described in the standard. Okay, now let's come to the second method. Correction of the measured sound pressure signal by using a filter. We are switching it immediately after our microphone signal arrives in our measurement system, and our goal is to compensate for the second linear system, each room here. So that should be actually 1. No? And that should be also true if the position between the test microphone and the desired evaluation point is different. Yeah, and here you see how we can calculate the compensation function. We have to inversely use each room, so that cancels out with a real one. It becomes 1. And we have to consider here the change of the distance. So it is not, it can be the 1 divided by R law. Then the phase shift is just determined by the time delay, and the amplitude difference is dividing or the ratio of the two distances, so that's simple. But if we are in the near field, if the test point is in the near field, we need actually a more precise value from the holographic processing. Because that's the whole idea. So that's very important. The 2 points are different, and here's the room influence in it. Yeah, and we can compensate room influence. We can compensate the positioning of the measurement point. Even if the angle is different, we can do that in many cases. And we can compensate also for some any other phase influences and amplitude influences. For instance, here's a half space, placing the loudspeaker here on the table. But it might be also possible to compensate if you are using a strange measurement setup, putting your loudspeaker in a stand or putting your driver in a different test box. You can use the same technology also for that. I'm coming to that very soon. But what is the workflow first? It starts usually providing with some reference response. We mean with a reference response accurate data. It may come from the holographic scanner, but there are some simple solutions also available. I speak about this soon. So we need that. And then we place our, actually we should use at least at the beginning the same speaker. So we have to do it here in our say reference standard condition and generating the reference data. And then we move the speaker into our bed measurement environment. We call it here in situ environment. So, okay, and here is your microphone placed, maybe also at a strange position, too close or in a different angle. And then we have to do a measurement, and we are calculating then the correction function by using the reference data. No? Okay, the reference data are usually required at the evaluation point RE. So that means if you change your mind where the reference point is, you can do it with the holographic processing in the last minute. Why? Because you get with the 3D measurement, with the holographic measurement, accurate data at any point in the near and far field. So that's quite convenient. Yeah, and then you have your compensation function you apply to the filter, and then you make your regular measurements. Yeah, that's it. And then you get here your direct sound, and you can apply any nonlinear distortion measurements, something like that. Okay, how to provide accurate data? It's very convenient. If you have an anechoic room, 50% or 30%, say it's not a problem, then you can do the measurements there. But if you don't have that, then you make an outside free field measurement, but you have to be aware of the error from climate, wind, and ambient noise. But holographic near field scanning is very convenient because you have all the data. So we like that very much. And now we are here on the first method. Actually, we will have 3 methods. I'm focusing at the moment of the first one, that is full compensation with full band reference. Here you see the abbreviation. Yeah, and we can from that generating simulated free field condition in any environment. So it might be a room, an poor anechoic room, a good anechoic room, it doesn't matter, or a very bad office. It might be also a test box, yeah, a tetrahedral or a QC end of line test box. It might be also a stand, you know? Yeah, we can then also generate simulated far field condition for all frequencies, but we need accurate reference data over the full audio band. That's why we need here a normal scan, and for this speaker here, it took me about 20 minutes. So for a larger loudspeaker, it takes longer. What is really important to claim all that, if you have here a test box, for instance, we assume that the air volume in the test box will not behave as an additional acoustical load and will change the internal state of the loudspeaker. That should not happen. But you see, it's very general, it's very convenient, it's very powerful. And how it works, here you see it. We have our reference measurement, here a transfer function href, at the evaluation point. And this point might be different than the measurement point. We are measuring in the first step this transfer function, we are dividing that, and then we have our compensation function. Very simple. You are, in a certain way, you take out the real room and putting that into the desired target environment. Quite simple. What are the pros? We are compensating for everything what is not right, and including room reflections and difference in the points, but we have some disadvantage. You need accurate resolution from the reference data, and it should be really accurate. And don't touch your microphone, don't touch the speaker. Even maybe Christian will show it later a little bit. If we are making a small change of 0.5 centimeter, something is wrong at higher frequency. So you need a tape to really bound your microphone on, or glue it on, tape it on the table. Yeah, that's different with the second technique, which is much more robust. That is, again, full compensation, but we are using only a low frequency reference. So we need actually less, we need accurate data, but only at low frequencies. And that's why we can use a shorter scan. We have shown it in the second session. Christian showed by limiting more or less the frequency band to 2 kilohertz, 1 kilohertz, we end up here with 7-minute scanning, which is quite convenient, and this is just sufficient here for our problem. That works quite nice in workshops. Workshops, I mean larger rooms, usually with some free space on the ground. That's perfect for this technique. It works here in my office. Yeah. So we need some distance to the boundaries. Here in my case, that's border-like. We have sometimes only 50 centimeters, so my laptop is very close to that, but it still works, you will see. No? Yeah, and here you see how we are doing our processing. We are measuring the reference transfer function only below 2 kilohertz. So that's here the crossover frequency. And we are using windowing to generate true data, or almost true data, at higher frequencies. And now we have complete data at all frequencies. We divide this by the total data without windowing. Yeah, also here H-test is significantly wrong and corrupted. And here we have our compensation function, and we can apply that. So it's quite nice, short scan. We need only true data, accurate data at low frequencies, and we are using windowing. And that's quite nice for positioning errors. You can move a little bit your microphone by 1-2 centimeters. If you redo the measurements, you can immediately compensate that with the windowing. So you always get accurate windowing data. That means if someone has touched your microphone, you have to start this full compensation measurement. It takes altogether 30 seconds. You will see it. So you can nicely compensate for that. But we have some problems. We need some distance to the boundaries, usually 50 centimeters, something like that. Yeah, here an example. The black curve is actually the low frequency reference, 7-minute scan. The blue curve is H-test here, very much corrupted by the room influence. By windowing, we can generate a relatively good result for that. And here you see the result that is the room correction function, which is quite complex. not only in amplitude and phase, but also in complexity. Here we have peaks up to 20 dB, actually over the whole frequency range. No? Yeah. Here Z are room modes, and Z are here early reflections. Yeah. And this is only true at one measurement point. Yeah, and then is the last method. This method uses also only the, or needs only reference data at low frequencies. And we can realize this with a short scan, 7 minutes. But this is quite nice for, I would say, small rooms, a little bit larger than that here maybe, but with some treatment here at the walls to generate approximately anechoic properties at higher frequencies. So that's, and that's more or less a poor anechoic room, cheap. Yeah. So that's completely sufficient for that. We are making only a compensation at lower frequencies. That's quite interesting. Okay, here you see the technique. So our compensation function is equal 1 at higher frequencies. We are doing nothing here. And we are calculating only the compensation function at lower frequencies by dividing the test signal from the reference signal. Yeah. Here, the evaluation point should be identical with the test point. That's the only disadvantage. So we cannot make a real far field, near field prediction. That's usually very much limited. So what are the pros? We need only reference data at low frequencies. That's simple. And this compensation function is only valid at lower frequencies, and it's interesting that it works for a wide range of speakers. So it is really a room correction function and not a room speaker compensation function. So it is really describes the impact from the room. Yeah. And of course, the microphone position. Yeah. But the microphone position is not so critical because at higher frequencies, we are not applying the correction function. So you can have, it's tolerant to a mismatch of 1-2 centimeters. Yeah. But this is a disadvantage. Evaluation point and test point shall be identical. Yeah, and we need the damping from the room. Okay, now we are not quite at the end. Now we are asking, we have now some compensation function, and can we apply the compensation function for similar speakers? That's actually our goal. And that is what we mean with a fixed room compensation function. Yeah, avoiding reference measurements on DUTs. Avoiding scanning, living with more or less a correction function which we have measured with other loudspeakers. But what are the requirements? First of all, we need a very well-defined hardware setup. It should be constant. We need a fixed microphone position. And the second requirement is that the DUT generates similar interactions with the room. Of course, the DUT, the loudspeaker, should be placed at the same position, but he should not radiate the sound to the rear side, or having the multiple tweeters or something like that, or multiple woofers placed on different positions or on the box. That will not work, 100%. And the DUT should have similar near-field properties if we are doing something with the second method to extrapolate this into the far field from the near field. Yeah, here one example. We have here 2 transducers mounted in very small baffles, and used here the 2 baffles in the near field measurement, and we found out, okay, at lower frequencies, we have a common large room influence. It's not perfectly the same, but we end up with similar room correction function. But at higher frequencies, already the two drivers are so different that we can never apply the same compensation function. No? But at lower frequencies, that's possible. But we can combine this with some windowing, and then we get still very good results. So that's the idea. No? So we recommend that you not take the reference, as the compensation function from one DUT. We recommend that you are measuring multiple speakers and checking or doing some statistics on the room compensation function, and then you can decide whether to generate a fixed compensation function. Here it is illustrated. You are doing your normal room correction function. You get that. You select only the low frequency part and forget the high frequency part, and then you are doing that again for different loudspeakers. You are averaging that, and if you find that the variance is relatively small, then you apply it to similar speakers. That's the whole idea. Yeah, and now here you see a new line. Here generating a fixed room compensation function for multiple DUTs or for other DUTs, for other devices. You see I put a red cross for the full compensation. This technique always uses or applies the reference over the full audio band, replaces the room by the desired transfer function. You get always a very special, very complex compensation function. You see it makes no sense to average that and to apply it to other speakers. But it works for the other two techniques, yeah, for lower frequencies. And the good news is you need no reference data. So then you believe that your fixed compensation function is correct, you apply it to other DUTs, and if they are similar, then it will work. And if you have some doubts, then it's time immediately to make a new reference measurement and to check that this principle is still working. And if you see, oh, that's a different speaker, then you generate just a second setup with a new fixed compensation function for this new class of speakers. That's it. You can handle that. Yeah, some practical tips how to use the fixed compensation function. I think what is very practical, create semi-anechoic rooms, which are small, cheap, good, above 400 Hertz. What is the most important thing here? Some damping, maybe not very thick, 20, 30 centimeters damping, that's not expensive. It could be a normal office or something like that, a small spare room. You need sufficient distance for your microphone that you are in the far field. And it should be quiet there. That's a nice thing. Then ground floor measurements are very interesting. Maybe in your workshop, you have some distance to the walls at a fixed position. So you need very well with a red cross, where is the microphone, or should the microphone be placed, and where's the loudspeaker. And then you make a compensation function for this workshop. Or similar DUTs, so you have one type of loudspeaker and you are manufacturing that, and you would like to calibrate your test box. And you know your test box is large, there is no loading from the air into the test box. Then you can nicely predict standard far field, free field condition, and you can immediately generate the final spec sheet for the customer. That is possible. So this is quite nice. Then also a small baffle is interesting, a really small baffle. Maybe you have seen it in the picture, 1 meter, 50 centimeter. It depends on the size. If it is a micro speaker, it could be 50 centimeters. Yeah, so that means you have a reasonable microphone position, and then you can use more or less windowing at higher frequencies to cope with the baffle problems. And at lower frequencies, you can apply more or less the reference curve to get rid of the baffle reflections. Okay, now it's time for the practical demo. Sorry for being a little bit late, but it's such an interesting topic and there are so many opportunities for applying this technique. So I made all those slides. This is again here our room. That's our measurement point. I have spoken about that. And we are starting, or Christian will start with a free field condition at 30 centimeters. We show what, again, the problem with the windowing, and then apply here the in situ full compensation low reference technique. But we are using here the complete scan to compare the windowing technique also with the full scanning technique and showing you, let's say, some problems also with the windowing. Then the next task is to generate not only free field condition, but also far field condition. So now our measurement point will be 1 meter. It's almost at the edge here of the table. It's a very bad measurement point. You get fancy, completely stupid results. You cannot use that, but we can nicely simulate that. Yeah, we are starting with the 20-minute scan using the full reference technique. And then we are doing the same with the 7 minutes data using only the low reference data. And finally, we try to make a room compensation function and to apply it for a second speaker of the same type. Yeah, without making any additional scanning. So that's our task today. And now it's time for Christian. I have to stop that here. Okay. And now I have to open here. Okay. A moment, I have to verlassen. Now. Aha, here it is. Yeah. A moment. Okay. Now you should see my DB Lab again. It's quite funny. The computer is here in my room, connected here to the measurement system. But Christian, who made the software, who is very familiar with the system, he will also give some commands to that, but I will operate more or less the measurements. So we are starting here with the first experiment. That's a simulated free field condition. But now, Christian, it's your turn.
Okay, thank you, Wolfgang. So, I mean, usually you would do a remote control of the computer at this point, but I do something different. I remote control Dr. Wolfgang KLIPPEL, which is, I think, a very new thing. And Wolfgang is like all modern personal assistants, voice controlled. So I will talk and hopefully Wolfgang will do what I want. Maybe we can first have a look in your office and on our measurement setup, because we have a camera in the office and maybe we can explain what we have set up here. So we can try to bring this in focus at first. So I hope you all have selected the correct picture, because we have now a second camera which shows Wolfgang and also this small blue speaker we want to measure. And you see 30 centimeters in front, there is the measurement microphone. So though for the Americans about 1 foot distance what we are measuring. And then we have our second point marked on the table. And we have an evaluation point, which is, as Wolfgang showed, right at the edge. And you see it was marked, and Wolfgang was very creative to set this point. And what have you used for this? It's just...
It's a 5-minute thing, some clay, and what I found here actually on my desk.
Okay, good. Okay, so this is finally the 1 meter measurement point where we interested actually in our data, but in Wolfgang's office we cannot go further away actually than this 30 centimeters. So all measurements we're doing are now performed in 30 centimeters, but we will try to use our techniques Wolfgang explained also to predict the sound pressure in 1 meter. Okay, maybe we start directly with the first measurement. So Wolfgang, can you please run the first TF measurement? Okay, what our first test is here, we are now actually doing a common thing. So we are compensating a room correction function exactly at the point where we are measuring. So we are at 30 centimeters, and the first task is we try to get a free field response at 30 centimeters. Okay. So maybe we just try to restart. I mean,
sure,
it's always the thing with live measurements. So maybe I just explain a little bit more what we want to do with the other measurements as well. So the first task is we just want to measure a near field free field response. And then in the other techniques, we will use our full scan, what we have done before, which took us 25 minutes to get also a frequency response in 1 meter, corrected with a full compensation curve. And then finally, from this complete scanning, complete directivity data, we want to go back to a simple correction curve. Now it looks better, yeah.
Okay.
We just see something, I just see something weird in the middle, okay.
I forgot to activate the Bluetooth device, sorry. Okay. No,
perfect. Now we got a frequency response. What do we okay. So maybe Wolfgang, can you just open the magnitude response window that shows the transfer function of this speaker? You have it open, just maximize it.
The magnitude?
Yeah, the magnitude. It's already there. Just
so maximize it.
Just maximize. So this is now what we see the response of the speaker at that position. So we see the huge room mode at low frequencies, but also at high frequencies, it's quite noisy. But we also have predicted a reference curve, free field curve with a near field scanner measurement at this position. So Wolfgang, can you please open this near field measurement curve?
Yes.
And maybe can you just copy it into the magnitude window that we just can compare both curves? Okay, so this is what we see here now is that we have finally at high frequencies almost a good match, but we see the difference because of the room influence here. So almost what we see here is even up to 10 dB almost problems. Okay, I mean, we can also have a look with our time frequency analysis to the same curve, just to see also the behavior over the time, to see what is the response of the room. So we see it in the energy time curve already that we have about 400 milliseconds decay. That's what we see here. So this is a time, there's a reverberation of the room. And Wolfgang, can you please also show the TFA time frequency analysis of this test point?
Okay.
So what we are doing with this module, we're now making a wavelet transform of the impulse response. So we should see very easily the room modes and also the reverberation. So I mean, what this diagram shows is on the x-axis the time, and on the y-axis the frequency, and the color is the sound pressure. So or the energy at a specific point. So the first vertical line, what we see is the main impulse, and then the rest which comes afterwards is the reverberation of the room. So we see at high frequencies an almost diffuse pattern, and at low frequencies we see some distinct room modes also here. Okay, so this is a part of the room, and this is what we want to get out of our measurements. So what is a common method that you just use a time window. So Wolfgang, can you please run the next TRF measurement? You can, yeah. So we now just do another measurement. We have already prepared a short window based on this time. And if you zoom in the impulse response, we have to make the window very, very short to get rid of all the first reflections. So they're coming very close. If you're looking at the time, you see we have about 23 seconds, milliseconds delay. This is almost the latency of the device. And then, yeah, just a few milliseconds later, our first reflection is coming. Okay. Okay, but we can use a short window to cut it out. But if we look at the frequency response, we see that we are losing resolution. So at the very high frequencies, it almost matches very good with our predicted curve from the near-field scanner. But at low frequencies, if we look at 300 Hertz, we're almost 3 dB off. And if we go more low, we even have not any data anymore, because this is now defined by the length of our time window. So actually, with a usually time window, we have no chance to getting a full band frequency response in this room. But for this, we have our reference function. What we're doing now, we calculate a compensation curve. We have a small module for this, which is just helping us with the calculation, but basically you can also do it by your own. So here we now are linking our test point, which you see here. We say, okay, we have a half space measurement in a measurement distance of 30 centimeters. And the distance to the first reflection, in this case, it was, I think the edge of the table is about 60 centimeters. Okay. Yeah, Wolfgang, please run the measurement. We can explain the rest on the curves, I think. Okay, can you please open the transfer function window in Maximize? Yes. So in this, actually, what is done what you see here is what is done in this measurement module. So we had the room reflection. So this is similar what we discussed before on the near-field scanner measurement. We now make a separation of room and direct sound, but just at this one point. And the thick green line, what you see is finally our free field curve. And you have a crossing range between the two yellow dashed lines where we change from the free field reference curve to our windowing. So though for higher frequencies, we use the windowing. For lower frequencies, we applied our curve. And the gray run in the background was our original measurement, which is called here in C2. So now we have run this measurement, and we already applied the compensation function to a TRF measurement. So Wolfgang, yeah, please open the TRF measurement. And this is now the result. We have applied the filter directly to the microphone signal. This is our compensation filter. You see it's, yeah, I mean, 15 dB from max to min. So we have compensated a lot in this office room. But finally, using this, we end up in the end with a clean transfer function. What you see here, so the transfer function is, I mean, what we expect from a loudspeaker, what also the near-field scanner measurement predicted at this position. But we have to say at high frequencies, we're not using the near-field scanner, we used the original measurement data windowed. And what's quite interesting, if we're looking at the impulse response and the energy time curve, that now our impulse is really, really short. We have shortened the impulse response a lot. I mean, you also see here that maybe a little bit unnatural behavior of the energy time curve. This comes because now we compensated anything, and there's also some kind of noise. If we would repeat the measurement, we would see in the energy time curve some noise flow coming up. But the impulse response will be still short because we compensated for the room response. Okay. But at this point, we now have only you have a free field measurement, but it's in the near field in 30 centimeters. So finally, what we want to do now with the next step, we want to also compensate for the distance. So finally, we want to get a compensation functions that gives us a free field response in 1 meter. As a reference data, we used also a complete scan here. For this loudspeaker, it was 25 minutes. And this gives us the full directivity in the full audio band. So we can easily generate a new free field curve in 1 meter. And now what we're doing now is we compensate everything. We compensate the room and we compensate the distance. So yeah, Wolfgang, please run another test measurement. Another measurement in the near field at 30 centimeters. Looks similar to the measurement before. And now please calculate the compensation function. And here we now finally end up with a complete compensation. You see in the transfer function window that we have also an offset between the two curves. So it's here about 16 dB, and this is as well the half space and the distance from 30 centimeters to 1 meter. What is this distance?
Christian, maybe we should also show that we are how we have set here this. We have the test point, which is similar like in the first experiment.
Correct.
But now we are here at the evaluation point.
Yeah. Yeah, we did no additional scaling. We just used the reference curve as it is.
So yeah, at this point, yeah,
because the reference curve is already the free field curve is already a full space curve in 1 meter distance, so we don't have to apply additional scaling here.
Okay. Yeah.
Correct. Okay, but if you want to do this, so finally we have to make always a complete scan, and this is maybe not a target because we want to get our compensation function much faster. That is why we now skipping to the next method, so which is also a complete compensation, but we are now using only a low frequency reference curve. So this was the 7-minute scan we've discussed in the previous sections. So this gives us a valid data up to about. So finally, now I can. The good thing is if I'm using the near field scanner, I can calculate an accurate curve for the low frequencies. So I can also calculate a 1 meter curve with all near field effects compensated at 1 meter. But at high frequencies, now I have to make an assumption. So I have to make the assumption that are in the far field, so I have to scale with 1 by r. That's finally what we see. We are having an evaluation point here, and this scaling, what we apply there later on, is an 1 by r scaling. So we say at high frequencies, I'm in the far field, and I just compensating the gain and the delay by the 1 by r lower. So Wolfgang, can you please run the measurement? Then finally we can have a look and compare it with our complete compensation. We showed also in the I mean, here it looks quite similar, but can you please now open the result transfer function module, so the result TRF? Okay, so this is now our free field curve in 1 meter, but at high frequencies transformed in the far field by the 1 by r lower. And we can compare this with our full compensation. Wolfgang, can you please do this? Can you please go to the object number 2? And please, yeah, give me this.
I take this one here.
Yeah, take this one, because this is now with also compensated for the near field effects, and here we have not compensated at high frequencies. So can you please maximize the curve? So yeah, and this is actually the difference what we now make an assumption. We say we're expecting we are in the far field, but we see some small near field effects here. So finally, so this is interesting. If you're making assumptions like the 1 by r lower, at one side you have to ensure you're in the far field, or you have to live with these small limitations here. So if we be 100% critical, we would say, okay, 30 centimeters is a little bit too close for this loudspeaker. We have to perform such a measurement maybe in a little bit further distance.
But Christian, I think here in the region of 2 and 5 kilohertz is more the windowing effect, correct?
This can be also, yeah, right.
Here we have used
no, because Wolfgang.
No, you have only you have taken in both cases the full reference.
Correct. So this is really now the difference between the one by Arlor and an exact model between near and far field. Okay. But as we explained, finally, the major thing, the major target is that we want to get a general room correction curve we can also apply for different speakers. So finally, we expect
Christian, we have forgot to show here the other time frequency analysis from this point. Maybe we should do that. I duplicate that, yeah.
Okay, we can do this, yeah.
And we are just selecting here the other test point operation. That's here the TRF 30 centimeters. This one, no.
You have to select a different operation, yes.
This one here, that was with correction function.
Yeah.
Import that and
start. Yeah.
Start. So,
okay.
Yeah, and here you see this is with free field condition, and that was the other one without. So it's quite.
So this was actually how that our filtering is not just shaping the magnitude; it's always really compensating for the room correctly. Okay. Now we
set here.
Yes, and now we just go to our last thing. We now make actually a very brave test, I would say. So we have this office room which has a lot of problems, and we had actually a very peaky and correction curve. But even here, we want to try if we maybe can use this curve which we have calculated now for a different unit. So, Wolfgang, can you exchange the speaker? Because we have also a different speaker. So we're now changing from the blue speaker to a black speaker. We try to set it as accurate as possible at the same position. So, and now we try to compensate with the correction function we did before this speaker. I mean, it's actually the same kind, but a different unit. So we start again with our measurement here. It's not turned on.
Yes, that's correct.
Okay, and Wolfgang, can you please copy the measurement curve from the blue speaker at first into that original measurement that we can now just, no, not the one with the uncorrected one, please.
Yeah, moment. Copy.
Yes. So
I do it now in red. Let's see.
So hopefully they match as closely. Okay, I mean can you please open this? Okay, I mean we see directly that at high frequencies they are some kind of different, these units. But at low frequencies, if we look at the basic curve shape, we see that they pretty much exciting room similar. So, I mean, we also see some minor disturbances, so which are caused by the room, and maybe we will see it later on in a little bit noise in the curves. But so far, we're not doing smoothing. We just try to use the data as honest as possible here. Okay, so now please open the property page of the ISC module. And we now need to import the room correction curve here. So here on setup, yeah, there we have to paste in the curve from the measurement before. Yes, from here. So this was now the correction curve for the. Maybe just copy it directly from the window. Yeah.
Only.
Yeah, you can.
You take it also complex, correct?
You can copy it directly from here. So. And now we can just paste it. Okay, so we are fine. And now please run the measurement. I mean, again, here we do a similar thing that we still using the window for high frequency. So we're applying this curve now only for the low frequencies.
Christian, you take only the real value, also the complex data?
we're taking the complex data for this. Or did we just use the real value?
Yes.
We have to check.
Yes.
Okay. Okay. Yeah, Wolfgang, you have to go to the export. Can you please go back to the and use of this the import export interface? Yeah, if you click there.
Now you see here the complex
Now we have
data
the complex curve. Correct. Thanks, Wolfgang.
Yeah. Okay. Now we go to that setup.
Yeah, and now you can paste it here. Okay, now we have.
But in a normal case, Christian, you would always have the same room correction curve here in this operation. So it would be part of the template, correct?
Yes, right.
So now I can press the button.
Yeah.
Oh.
Sorry, it has a problem. Can you give me control? I think we just we can also go with the window.
Yeah, you have control now.
Okay, we can also go with the curve from the window. So what we can do from here, I mean, we can also apply a real curve, but finally the module will automatically make a phase assumption, will reconstruct the phase. So it's also possible, and it's also quite a stable approach if you're using general correction curves. So let's see if we get another bug or if it works. It's a nice thing on live measurements. Okay, let's see. Okay, it works so far, and now the interesting point comes if we getting a result here. And maybe I remove the old data. Can you do it, Wolfgang? So the copied curve.
And I take the measured one, yeah?
Yeah, you can. But the measured one is now is now from the absolute level different because we have compensated also for the distance here. That's the point. So it will not. We can look at the curve shape, but the absolute level will be different. This is now again the 16 dB from the half space and from near field to far field.
But what is really exciting is using without scanning, using the data for the room correction from a different speaker and apply it to that. That the error here in this region is quite reasonable. It's in the order of 1-2 dB, but the room influence is quite larger. No?
And what we also see here now, we have not applied any smoothing, and this is now really a little bit caused by the very critical room environment. So if you can put a little bit of damping in your room, you can get also rid of this really huge disturbances. So it's in the end noise, a matter of signal to noise, because we had some strange cancellations here. So if you apply a little bit of smoothing, this is
well, so let's do that here.
Oh yeah, you can do this maybe too.
A 20th of an octave for smoothing, I think so. So then it's almost gone. But it's still a very high resolution here.
Yes.
What is interesting, I should make a mismatch of the speaker, and maybe we should try what happens, correct?
Yeah.
So that means I duplicate that. That's our, say, optimal position. And now I change a little bit, only by 1 centimeter. I shifted the loudspeaker and I do it again. Naja, it's not so bad. The reason is at lower frequencies, it makes no harm because the wavelength is large. And at higher frequencies, we are using anyway our windowing. No. So it's still relatively robust.
Okay, maybe what I can add here, I mean, finally, we today focused here on the fundamental, and on the fundamental, maybe it's also sufficient to adding maybe such just a magnitude curve, but finally we need especially this complex filtering for further analysis to measuring also harmonic distortion correctly. But I think this will be covered in the next sections.
So, okay, now, do you see the screen, Christian? Is this fine?
I still see the DB Lab, so I think you want to make a summary on your slides, correct?
Yes, yes. Then I close here the... I have spoken about that. That means measurement condition, optimal standard measurement condition can be simulated, and there might be a difference between the measurement point and evaluation point. We can always do that by filtering the microphone signal. That should be a complex transfer function because we are fixing not only the amplitude problems, but also the phase problems. That's important for nonlinear analysis of the distortion. This correction function can be generated in the last minute in situ, depending on the position of the microphone and if you would like to change also the evaluation point. So that can be done quite quickly if you have reference data at the evaluation points, and very convenient is to use the spherical wave model with the coefficients. You can nicely calculate that. We have done this here in our measurement always in the background. Yeah, what is the goal of that? The goal is to have relatively good rooms or sufficiently large distance that you can live with the windowing and that you can compensate for selected speaker set with a fixed room correction curve. That's the target. If you have some doubts, you can always repeat the process and ensure that your room correction is still valid. Yeah, what are the next topics? Now we are ready for doing some nonlinear distortion measurements, large signal measurements. In the next session, we measure the maximum SPL. We speak a little bit about the stimulus. That should be a broadband test stimulus representing the program material. We have to speak about the consequences or relationship with the long-term power testing, because that's a very important criterion that the loudspeaker can handle that. And we show the calibration routine, which takes a few seconds. So that's the next time. And now we have still some time for discussion.
That is fascinating. Thank you very much, Wolfgang and Christian. We've got a few questions coming in. I think I just saw somebody raise their hand. Now, this is a new GUI, but for that person who's raising their hand, go to your Q&A tab and please put your question there. So one of the overriding questions that we're seeing early on is, when is this technology going to make it into the QC portion of KLIPPEL? We know that we have production noise immunity in QC, but maybe you want to explain how this is a little different than PNI, and if this will make it into the QC portion, or into the QC portion of KLIPPEL. That's right.
Yes, that means the point is generating such a room correction curve is the first step, and we have spoken about that. And the second step is to integrate that into the QC system. Of course, we have already a calibration function in the QC, and we have Robert Werner with us. He is managing here the whole hardware, so I asked Robert directly to answer this question.
Wonderful. Is Robert going to answer that? Robert?
No. You should be able to hear me now.
There's Robert.
Hello. Hi.
So a picture of Robert. Robert, we need video on you.
I hope I can switch between the two cameras here, but I can try.
Right. You get a little bit of an echo too.
Yeah, I'm sorry, that's me.
That's okay. There's Robert.
Hi there. I was not prepared for that, but
That's okay.
that's fine.
It's a live webinar, buddy.
Yeah, so I have to be part in it, like really live. So I think there are two aspects that Klaus has been asking for. So one thing is how to correct my frequency response and distortion to make it look like it was measured in an anechoic chamber. So with certain limits, this is possible in the QC. And so we have a magnitude correction curve that you can activate, but the full complex compensation is not included yet. So this is something that we'll definitely look into in the future. And the second thing is the removal of any disturbing sound from the outside. So it is completely true that with the near field scanning system, we measure on a full surface and we can separate outgoing sound from incoming sound, but we assume that the incoming sound is reflection, so that it's the same signal every time and every measurement point. So actually we're scanning the whole surface and assuming the same signal all the time. So if we would do this live, we would need to have like a sphere made of microphones, and then we could maybe separate even disturbance from the direct sound. So for noise removal, this will not really work. So this is always a very complicated thing, and that's why we're still relying on our sweep test and cutting out the bad parts, the disturbed parts. We can clearly identify that, and so we merge together a valid full response. I hope this answers the question. If not, please let me know.
And I imagine there needs to be particular attention paid to your environment. I mean, it's best to have your DUT in a particular jig and your microphone in a specific place if and when this is implemented. We want all things lined up consistently, test after test.
Sure.
Right.
Yeah.
Okay, well, I don't see too many questions coming in. We appreciate you all showing up again for these webinars. We'll be here for you again next Wednesday, 5 p.m. in Germany, 10 a.m. here in the Midwest in CDT. I'm going to ask Wolfgang and Christian if they have any final comments or summaries to discuss before we sign off.
Not from my side, thanks.
Also, not from my side. Many thanks for your attention.
Wonderful, thank you. I did want to address the fact that one of the difficulties we had with Webinar Jam, or Web Jam, I guess I shouldn't be calling them out by product, but it's interesting as we're jumping to this new platform, is delivering to you a video that is that you're able to fast forward and rewind to. We are doing some editing and some recalibration of some of those videos, and those will be up online for you very soon, so you can share them with your employees and then be able to rewind and fast forward. So watch for that, although I believe we'll deliver a video recording of this too shortly thereafter. But afterwards, we're taking care to edit them and make some nice things for class consumption. All right, from Minneapolis and St. Paul, I'd like to say goodbye. Thank you, Wolfgang and Christian, and we'll see you all next week.
Bye-bye.
Thanks. Bye.